So where do we go from here? Well, the next point that we come to is quantum mechanics, and this is where our ideas behind the Bohr model have really changed. So why? Well, why do we have to change the Bohr model? Well, what we said last day is that Niels Bohr model could only predict the bright line spectrum for hydrogen. Now that's problematic because clearly there's more elements than that. Also, what we see is that there were new emergent ideas and results being found by scientists such as de Broglie and Schrödinger, Heisenberg and Pauli that changed the way that scientists visioned how electrons would behave around the nucleus. So, the first one that we look at is Louis de Broglie. And in 1924, he proposed that electrons exhibited dual properties. That is, they can act both like waves, in that they can be reflected and diffracted. In other words, they can be focused. That allows us to think about them and use them in things like electron microscopy. As well, they can be thought of as being particles or packets of energy. And this way we use them or apply them in producing an image on an old school TV tube. Because of that, electrons can no longer be thought of as being charged particles in concentric rings at fixed distances from the nucleus. So we had to envision, well, if they're not at these fixed distances, like Niels Bohr had envisioned, and had so accurately predicted the results for hydrogen, well, where could they be? Well, Heisenberg in 1927 reasoned that if you can't predict with any certainty what an electron is, then it's also impossible for you to know simultaneously both the location and the momentum or speed at which the electron is traveling at the same time. Now that's problematic because obviously we want to know where the electron is, we want to find out where it is, but if we do, then we can't say anything about its speed. Now that might not seem important to you, except that we know that electrons must be moving or they would be collapsing into the nucleus. We also know that there has to be a restriction on how fast they would be moving, otherwise they would just fly off of the atom. So the fact that we can't know these two things simultaneously is very important to us. And that's what became known as the Heisenberg uncertainty principle. Now along came E. Schrödinger, and he developed a wave mechanical model of the atom, which gave us a different concept of the atom and its electrons. And what it said, and what he theorized, is that the position of an electron around the nucleus could now be determined in terms of probability of finding an electron at a certain place around the nucleus at a certain time. So we can't say exactly where an electron is, but we can produce mathematical models that say with some amount of certainty that an electron should be within a given volume of space. This region, where there's a 90 to 95% probability of finding an electron, is now called an orbital. So now we don't think about electrons as being found at orbits or shells, but instead they're found in regions of probability called orbitals. To locate an electron in an atom, chemists use a former address called a quantum. And to describe that address, we use a series of quantum numbers. I've got set up here in different colors representing different types of those quantum numbers. The first is the principal quantum number. We would write it with the letter N. And that tells us the energy level of the electron. Really, this represents a distance from the nucleus in our mind. The second one, which we see here in blue, is the type or shape of the orbital. Again, there's different types of shapes of the orbitals, and depending on the shape, it determines the energy of those orbitals. There's S, P, D, and F orbitals. Again, more on this later. There's also an orientation, so how it aligns along the X, Y, or Z axes, or maybe in the case of some orbitals, they're in between. And finally, there's an electron spin. And what Pauli theorized is that every orbital can hold a maximum of 2 electrons, but in order to have that, they must spin in opposite directions. To show the opposite directions, one electron is a plus half. We would draw that as an up arrow, and the other one is a negative half. And what that means is that there's 2 possible electrons in any one orbital, but they must have opposite spin. And again, this is called the Pauli exclusion principle. So just to review, orbitals are regions of probability where 90 to 95% of the time an electron will be found around the nucleus. And according to Pauli, only 2 electrons can exist in any one orbital, but they have to have opposite spin. Remember, a plus a half or minus a half if we were drawing it an up arrow or a down arrow. So that's to say that in any one energy level, electrons can have different orbitals, or can be found in different orbitals rather, but those orbitals have a maximum that each can hold. So let's look at the different kinds of orbitals. The first simplest shape of orbital, and when I say simplest shape mathematically, that really means lowest in energy, is an s orbital. S orbitals are spherical in shape, which means they're omnidirectional. If you turn them by any amount, you're going to end up with the same volume or space in 3 dimensions being occupied. Because of that, you can only have one orbital at any one energy level, or in our minds, at any one distance. Because every orbital type can hold 2 electrons with opposite spins, any one s orbital can hold 2 electrons. And again, like I said before, because it is the simplest shape, this means that it's the lowest in energy. The next shape that we deal with is a p orbital. And a p orbital is a dumbbell shape, which aligns up along the x, y, and z axes. Because these p orbitals geometrically have to be aligned along the axes, there are 3 possible orbitals in any given energy level, except for the first one because there's not enough space. Each p orbital, like any other orbital, can hold a maximum of 2 electrons. So being that there's 3 orbitals, every energy level's p's can hold 6 electrons maximum. D orbitals, as we can see, these are getting increasingly complicated. There are 5 different d orbitals. We don't have a specific name that we call them, but I sometimes liken them to a clover leaf. There's 5 different d orbitals, each of which can hold 2 electrons for a total of 10 d electrons in a given energy level. And these start to appear at the 4th energy level, as we'll see in a minute. Now, the d orbitals are much more complicated than the p's, which were much more complicated than the s's. So you can imagine that the next shape will be even more complicated. And looking, because mathematics quite often has patterns to it, when we looked at the s there was 1, with the p's there were 3's, with the d's there was 5, and now with the f there are 7 orbitals, which can hold, with 2 each, a maximum of 14 electrons. Now these don't happen to appear until getting into the 6th energy level, and that's because there's a balancing act, as we're going to talk about in a bit, that determines the exact energy of a given orbital. Now this model of the atom is based upon the work of many brilliant scientists and upon some very, very complex mathematical equations. So far, this method can adequately explain past and present properties of the atom, as well as being used to predict future events, which makes it, as a mathematical model or any kind of theory, a very solid theory. Now, moving on and looking at how we can use those ideas in writing electron configurations. We have to remember that 1, the probability of an electron being found 90 to 95% of the time is the way that we describe an electron's location around the nucleus. And we place those electrons now into orbitals, volumes of space. There is a distance from the nucleus where the probability of finding an electron will be the greatest. That's called the average radial distance, or the orbital radius. What we see is that there eventually, as you move further from the nucleus, there will be positions where mathematically there is 0 chance of finding an electron. And at those specific locations, we call that a node or a nodal region. So looking at this particular diagram, we would see that this position there, or these positions, all represent nodes. And that's because they have no chance of finding an electron at that particular spot. If you look, though, at this position, or on these diagrams, this one or this one, those represent the average radial distance because that's where we're most likely to find an electron. All of that gets put together in what's called an energy level diagram. And the energy level diagram is a way of showing the relative amounts of potential energy that electrons will have if they occupy a particular orbital. What we also have to look back on is the fact that what we talked about last day is that similar to or just in alignment with the staircase model, these electrons can be found in positions at distances from the nucleus. And the further from the nucleus you are, the greater the potential energy that those electrons would possess. The energy level diagram shows the relative energy of the orbitals. This does not show you the spatial arrangement. So the 1s is not necessarily in one volume compared to the 2p. This is showing you how high they are in energy. Now, according to quantum mechanical model of the atom, the energy of any given electron is determined by two things, and there's a balancing act here. One, it's determined by the distance that that orbital is from the nucleus. All the 1s will have the same amount of distance, the 2s will all be at the same distance, the 3s are all at the same distance, and so on and so on. The second thing that we see is that the shape or complexity of the orbital also contributes to the energy. Where the more complex the shape is, the greater in energy it is. The simplest being the s orbitals, so those being the simplest are the lowest in energy. The 3s would be lower than the 3p. The greatest in energy would be the f's, greater than the D's, which are greater than the P's, greater than the S's. And because of that, those would show you as well that the F's would be, for example, for the 4F, much higher in energy than the 4D, than the 4P, than the 4S, even though those things are all at the same distance from the nucleus. Now, electron configurations for any atoms or ions can be determined if we know two things. One, the number of electrons that are in the atom or ion. For an atom, we know that the electrons is the number of protons, which is defined by the atomic number. For an ion, we know the number of electrons is the number of protons minus the charge, because negative ions have more electrons, so when you subtract a negative, it gets higher. Positive ions have lost electrons, so they would have less. The other thing we need to know is the relative energies of the orbitals, and that's where we'll refer to our energy level diagram. Electrons are added to consecutive energy levels starting with the lowest energy level first. This is called the Aufbau principle. When we add them, every energy level gets filled before we move on to the next energy level, meaning that, again, remember that each orbital can hold a maximum of 2. That lines up with Hund's rule. On the diagram of the energy level diagram that you have, I represent them using circles. In this particular diagram, it's shown with spaces. Every space or circle that's given can hold 2 electrons, one going up and one going down. The orbitals of an energy level are grouped together when they're written in an electron configuration, and we'll talk about why that is in a bit. All the orbitals starting with the same principal quantum number need to get grouped together. That's not in alignment with what your text asks you to do, but I would request that you line them up that way, and we'll talk about why that is later. So I'm going to stop at this point. There will be a second video section from today, but I think that having that one separate so you can watch it over and over again is to your benefit.